yes, the title of this talk is Imaging from the Inside Out, and it encompasses a series of papers, I guess 2 papers that are published and 1 paper that we're still working on. And along the way, we acquired collaborators and we all played musical chairs. So Jeremy Hoskins was involved in this project, and Howard Levinson and John Schotland. So here we go. So a less flip title for this talk could be Super Resolution and Inverse Problems with Internal Sources. So how do you image from the inside out? Here's the overview. I'm going to give you my understanding of some of my collaborators' previous work in this area on near field inverse scattering and microscopy. And then I'm going to talk about where Howard and Jeremy and I came into the picture, so to speak, with internal sources and super resolution. Okay, so I want to emphasize that this is work that John Schotland did with his former postdoc, Scott Carney. And they were motivated by nanometer scale imaging, and they built or proposed, I'm actually not sure, proposed a near field microscope that worked, as you see in the picture. You've got a sample surface and a cantilever with a little tip on it, and a laser that is measuring how much this tip goes up and down, and you get feedback and whatnot from the vibrations of this. And I do want to emphasize that I spent a while reading over some of these papers, but I am not involved in this work. And the mathematical part of this problem is that you've got an incident wave, wave coming into this object, and you've got this probe that is very close to the object that can move around. And sorry, was that a cough or a question?
It's a cough.
Okay, great. Okay, so these microscopes are they're okay. The far field resolution of these microscopes is the wavelength of the light divided by 2, and the sub-wavelength information, the really small scale features, are carried by the evanescent waves. Okay, so I'm going to wiggle my fingers. The evanescent waves are the ones that die out in the near field of the sample, and you can do some image reconstruction. So this is from some of their papers. So here are some more image reconstructions at the various wavelength scales. The problem is that as an inverse problem, this is horribly ill-conditioned, and you can't get very good, you can't get fantastic resolution as a result. And just to give you a picture of, what does it mean to resolve two sources, under an optical microscope, this is what, sorry, I also have lost my mouse in this. So I'm going to point at the screen, but imagine me pointing at your screen. So, if you've got 2 sources that are fairly far apart, then, they're well resolved, but then when you get them close together, they're not. And, trying to reconstruct from these evanescent waves is quite difficult because, they die out. So you get lower resolution images than you would want. And, their work, oh gosh, it must date back 20 initially, 20 years ago. they realized that the math is sort of the barrier here, and in order to overcome this, you need some sort of new physical idea to deal with the stability and the resolution. And so that's where the idea of imaging with internal sources came along. And the idea is that if you had, so I'm going to play off internal versus external measurements. Okay, so typically in one of these optical systems in this microscope, you have external measurements, outside of this object that you're trying to image, and your measurements are taken outside the scattering medium, and it would be fantastic if you could actually measure inside the object. You would really change, you would fundamentally change the inverse scattering problem. You would fundamentally change the mathematics, and you could then determine the scattering potential directly from the governing wave equation, and the inverse problem would be well posed, and you could do reconstruction with high spatial resolution. Except, in general, we can't put sensors inside an object. What we can do is notice that we can flip the role of detector with sources. And if we, using the principle of reciprocity, if instead of having internal detectors, we could have internal sources and then measure externally, then we would get the equivalent of internal measurements. Okay, so this is a new physical idea. Where do we find such sources? Well, it turns out that there are chemical compounds called photoactivatable fluorophores. Okay, this is a tongue problem today. And it turns out that PAM, these are photoactivated localized microscopy. It is a form of super resolution microscopy where the resolution is like on the order of 10 nanometers, or wavelengths divided by 50. And fluorophores are chemical compounds that if you hit them with light, they will re-emit light after absorbing what you've hit them with. And if you stick them on various cellular structures and get them to light up, then you can easily identify what is lit up amidst what is not. And in fact, you can localize these if you light them up sequentially. So at time one, so if you've got three very close together, you light up one at time one, you light up another one at time two, and then you light up the third one at time three, and then superimpose all the images on top of one another. Then you get the actual image, and you get these three fluorophores all clustered together at a resolution that's much finer than you could do if you tried to get all three of them at once. And this is fantastic. It's a fantastic idea. It won the 2014 Nobel Prize in Chemistry. This is Eric Betzig's work on PAM. It's a fantastic idea. There is, however, more information in these physical measurements than is used simply by stacking together these images. And these fluorophores are going to be our internal sources. So here is the physical idea. It is to use the photoactivatable fluorescent molecules as the internal sources and use them to solve an inverse scattering problem. So this is assuming that you have the locations of the sources, and then you measure outside of your object, and then reconstruct inside the object. Okay, so Yes, I'm going to derive this like it's a claim. One can make this more or less rigorous. And this idea will yield an algorithm for reconstructing images from these types of measurements. I don't currently make any great claims about the algorithm. What I do have is pictures. So assuming that we know the amplitude and the phase of these fluorophores, which actually is available via IPAM. IPAM was cooked up after PALM, and the I stands for interferometry. And so if you know the amplitude, the phase, and the location of the sources, then you can solve stably for the susceptibility of the medium inside the object. So, you know, we're just going to do a 1D derivation here. And we're going to assume that the electromagnetic field is scalar, and then we can derive the optical field from these that is emanating from these sources. We can determine that the field is given by this integral equation where the Green's function is known, and we have the background field, of course. And then in the far field from the far field from the scatterer, this field behaves like a spherical wave, and the scattering amplitude is given by this integral that depends on the susceptibility of the medium. This is what we're trying to figure out. So if we consider scattering data of this form, where we know x0, the location of this fluorophore that's emanating, we know its phase phi, and we know its amplitude, then we can get an inversion formula for the susceptibility of the medium. And this means that we can get a local within the medium reconstruction of the susceptibility, which is stable. It has Lipschitz stability of this form. Okay, so in one paper, we took this one simple idea that if I know all of this information about my internal sources, my fluorophores, I know exactly where they are, I know exactly their phase, I know exactly their amplitude, I turn them on, I turn them off, I collect measurements, then we are able to reconstruct not only the parts of the spiky neuron that we use as our example, but also we're getting, if you will, sort of a complete picture inside the object. And so that is the first paper that we did, which is place a bunch of sources and reconstruct the susceptibility. Okay, reconstruct inside the medium. So we took as an example this Spiny neuron from a standard database, and here are the dimensions of this cube or rectangular prism that contains this Spiny neuron. We had 225 detectors in the far field, and we placed 200 internal sources inside this prism. I'm going to walk you through the various configurations that we tried. This, you can see below the number of voxels for the forward problem and the number of voxels for the inverse problem. And for the examples that I'm going to show you, we added a small amount of noise, so 1% Gaussian white noise. Okay, so the first kinds of reconstructions we did were to place the sources randomly on the neuron itself. And you can see we actually get pretty good reconstruction of the entire neuron, not just the map of where the fluorophores are. Oh yes, this I should have said. I should have emphasized when looking at the palm pictures. So the palm pictures, what is imaged is only the fluorophores. And so if they are stuck to something, then you see the structure that they sit on only because that structure is lit up by the fluorophores. Just like here, I'm going to see 3 of them together, but I'm not actually going to see anything around these 3 fluorophores. Okay, so what we're doing is using these fluorophores as like little flashlights to see around this object, not just to image the source sitting on the neuronal structure. Okay, so hopefully with that made clear, that explains what you see down here. It's a little blurry, but it's not bad actually, and you're resolving more than simply the structure on which the fluorophore sits. So excuse me, my mouse, I don't know, in this play mode, the mouse I can't see, but if on the image on the upper right, you can see there's a tendril sticking out, and there's one fluorophore just right at, almost where the tendril attaches to the body. And, if you were just using a palm imager, all you would see is that spot. But because there is some light there, you can see in the reconstruction below, you can see sort of a shadow of this other tendril. It's not bad considering that there are no fluorophores actually on that except right there at where it's stuck. And so, it's actually not bad. This is 200 sources placed on the neuron. You might ask, what happens if I place them randomly throughout the prism? And this is 200 sources placed throughout the prism. I'm just going to flip back and forth so you can sort of see. Yes, there is a difference. Whether one is better than the other, I don't know. This one looks to be sort of less noisy, smoother. Anyway, some of this may be the artifact of my screen. Okay, so you might ask, how few sources can we get away with? I don't know if 200 is a lot for this sort of object, but here we are, with decreasing number of sources, 150 down to 10, and it degrades, which is what you would expect. It degrades, I would have said, mostly gracefully. In the paper, we have more quantitative measures of how this degrades, but I wanted to show you pictures more than anything. Okay, we also ran this problem on 3 spherical scatterers to really get ideas of where this method works and where it breaks down and how it breaks down. So we've got 3 spherical scatterers, and each image here is a slice through the medium that's holding the 3 scatterers. And I've put all of the information about the setup of the experiment over here on the right. What is the size of the field of view? We've got 2 scatterers with 1 value of contrast and another scatterer with a second value of contrast. We put 150 randomly placed fluorophore sources. Again, just to remind you, whose position, amplitude, and phase we know, and then 169 detectors in the far field with some noise. And so well, you can see the images for the reconstruction. This is also a configuration where we can gather more quantitative results, and we can see how good a job we are doing at resolving some of these sharp edges, where we should have the scatterer, and what the profile looks like that gets reconstructed. It's not too bad. Okay. Again, more experiments to determine what happens if we don't know the positions, the phase, or the amplitude particularly accurately for these sources. If we have a single scatterer, again, these are slices through a single scatterer. If we have accurate measurements of where the sources are, we get a beautiful reconstruction. And then if we know the source's position up to 1 voxel, how well do we do? How well do we do if we know it up to 2 voxels, etc.? So, this is great. This is it's a good first paper. It's a good proof of concept for something that I'm going to introduce next, which is, suppose I know the susceptibility of the medium. Could I use that information to determine the amplitudes, phases, and positions of the sources? So assume that I've got my field measured at M detectors with these positions x1 through xm, and assume that there are n sources with the corresponding amplitudes, phases, and positions. Could I figure out from the external measurements, knowing the susceptibility, where the sources are and their various other parameters? So I claim yes. One would solve a nonlinear least squares problem to find these parameters of the sources. Again, using the derivation from before. And so now this gives me an idea, and that is to iteratively solve, go back and forth between first finding where the sources are, and then reconstructing the inside the medium, the susceptibility, and then using that information to refine my estimates for the parameters of the sources, and go back and forth, iterate back and forth until I've converged and hopefully get a better picture inside the object that I'm trying to image, a better picture than simply using the information about where the sources are. I mean, and not just simply taking stacks of images with just a few sources lit up in each one and smashing them together. So here's a cartoon picture. So this is half a cartoon, half an actual reconstruction, beautiful computer simulation. So again, this is a slice through one scatterer with some number of randomly positioned sources, and the true source positions are in orange, and the reconstructed source positions are in sort of turquoise color. We make a guess at these sources. We use them to determine the susceptibility, and we get an image. It's okay. It's not fantastic. We use those measurements to estimate or refine our estimates of the source positions. What do you know? They get a little closer. We use those to refine our image of the scatterer, and notice it looks better now. And we do this a couple of steps, and at least in a cartoon setting, we get a beautiful reconstruction and pretty accurate estimate of where the sources are. Okay, so one can turn this pseudocode. One can turn this algorithm written out in words into pseudocode. There are There are some numerical roadblocks that have to be circumvented or dealt with in order to make this really work. So in order to show you some of these pictures, I'm going to tell you, exactly what we did in order to collect the appropriate measurements, how to generate the appropriate measurements, et cetera. And, how did we, why do we get these funny, ringing spots, et cetera, in the inaccurate reconstruction? So I'm going to show you, I think it's a couple of experiments where the domain has dimensions, it's a 2D thing, half the wavelength of light. We're going to have 1,000 sources randomly distributed throughout our medium. And we have to generate forward data in some way. This is all, computer simulation. So we solve the wave equation using a coupled dipole method in 2 dimensions. And then we're going to measure the scattered field in the far field at 20 equally spaced angles. Again, we add 1% Gaussian noise. And we decompose the field measurements, or we fit them to a tensor product basis of Legendre polynomials, which is why you get these funny artifacts there. This also allows us to use spectral differentiation so as to implement the inversion formula. So that's why we used this. I will also say that quite a bit of care went into exactly how to solve this nonlinear least squares problem. And I should say care was taken not by me. So I can't tell you exactly the details. I believe they tried some sort of Newton method, and what exactly the details were of that, I don't know. This is Jeremy and Howard. They are whizzes at this sort of computation. So, okay, here is an example reconstruction. We've got a bunch of things that look like straws to me. And, we place we place 1,000 sources randomly distributed throughout this medium. And then we do this, alternating reconstruction where we, with an estimate, with a guess of where the sources are, we reconstruct the medium. Then, knowing the medium, we refine our estimate of where the sources are, and we iterate like this. And you can see after 5 iterations, it's not bad. This reconstruction is really not bad. Especially when you consider that we've just thrown fluorophores into this object and lit them up, and they're like little flashlights seeing inside. So I believe I am almost at the end of my talk. I think this is the last slide. So excuse me for being quick. So I'm going to give you an example of how this algorithm, how this method breaks down, or under what conditions it breaks down. So again, I've got 2 scatterers, and I turn up the contrast between the background and the scatterers, and you can see that at 50% contrast, I'm doing pretty well. But this method breaks down by the time I get up to 200% contrast. And you can see, excuse me, on my screen, it's the orange line that is just garbagey by the time you get up to that high contrast. Oh, no, I'm not. This is the last slide. So you might ask, okay, fine. These examples are all sort of proof of concept examples. They show the limitations and the possibilities of this method. how do you do on that spiny neuron? So let's go back to the original example, and let's take the spiny neuron. Let's throw 1,000 fluorophores in here randomly. And what happens after we do, 5 to 10 iterations of this sort of cakewalk type algorithm? What kind of reconstructions do we get? They're not bad. So I'm going to do like a lens A versus lens B trick on you. So okay, so here is the reconstruction where we don't know where the fluorophores are. Okay, hang on. Sorry, there's a delay. Okay, here's a reconstruction where we do know where the fluorophores are, but they're placed randomly. Okay, now, this is not a great comparison because we had 200 sources here versus 1,000, but, okay, hang on, another delay. But I claim this is not bad. It certainly looks, reasonably comparable to the 200 sources placed randomly where we knew exactly where they were. So I think that this is pretty good evidence that this is pretty good numerical evidence that this is an interesting idea to try. It definitely needs to be explored more. And I can definitely tell you that this algorithm requires some care. So let's put it that way. So I'm sorry for being so short on time. That is the end of my talk. Do you have any questions?
Yeah, thanks, Anna.